PhD student at the University of Texas at Austin, Institute for Geophysics, working with Donald Blankenship. My background is actually in physics and robotics. I decided that Antarctic science was more fun than self-driving cars. I had originally planned to treat this talk as an advertisement for my poster, but then Matt encouraged us to think bigger picture. So I'm going to give a talk based on my thesis plan, and only briefly explain how the poster I'm presenting here is a small step towards the start of it. So at the last IGS CRISP meeting, almost every talk started with one of these two figures, so I'm just going to put up both. And anyways, researchers have established that most of Antarctica's mass loss is currently occurring through its ice shelves. We also know that the grounding zones are retreating, in some cases rather quickly. But we have not yet gotten to the point of being able to predict their behavior. And these figures show the retreat of ice shelves in the Amundsen Sea and Totten over the course of about 20 years. So I want to better understand the gradients of behavior, particularly in the context of a pinning point leading into a submarine basin. Of course, with weights, I'm not even convinced that's going to be applicable in the future, given what's happening to its ice shelf. But anyway, we hypothesized that subglacial hydrology may be involved in a feedback loop that helps to control the grounding zone behavior. The idea is that subglacial discharge affects the pattern of ice shelf melt. The resulting changes in ice shelf geometry changes stress due to the upstream ice, which in turn has the potential to change subglacial hydrology. So that's a nice, tidy concept, but I'm not even sure whether we would expect to see positive or negative feedbacks. So I plan to look into process modeling for how channels, canals, loose cavities, etc. might respond to changing water availability and ice stresses. And testing these models is going to require improvements in observational techniques. So what are we doing right now? Among other things, satellite insight altimetry have been used to localize grounding zones based on pressure, AUVs, studying them from below, airborne radar from above. So this figure shows an airborne radar-derived basal geometry of vast locations under the Pine Island ice shelf, and nearby AutoSub data has been very valuable for confirming the interpretation of the radar data using direct sonar measurements. However, the state of technology still isn't to the point where we can see robots all the way to the grounding line. Along with the need for more sophisticated control software, a major limitation is a trade-off between optimizing mechanical designs for range and for high maneuverability in confined spaces. From above, we're using ice penetrating radar to characterize the ice bed and ice-ocean interface. This allows us to infer properties of the interface in addition to just obtaining its geometry. For example, Dustin Schroeder looked at the anisotropic specularity of the bed over the Thwaites catchment and observed that the distributed water system in the interior changes to a channelized system downstream. I would like to look at the grounding zone at pinning point in more detail and connect the subglacial water organization to feature on the shelves. However, a perennial problem with interpreting ice-penetrating radar for high-resolution topography is the existence of off-nadir echoes. Constraints due to aircraft geometry and the ideal wavelengths for sounding ice lead to a radar beam pattern with strong side lobes. For example, here's a radargram from near Dome Sea, where there's multiple bed-like horizons. We instruct the undergrads interpreting data to choose the first return as the bed, but it's possible this return is doing an echo from the side, and the nadir bed is lower. This interpretation problem is even harder for floating ice, where you have basal crevasses. Crevasses are a lot of fun because the tip is a point scatter, and the base is a corner reflector, both of which are really bright radar targets from a wide range of angles, leading to some interesting radargrams. CREASIS has been attempting to solve the problem of off-radar discrimination by mounting multiple antennae under each wing, recording data from each antenna independently, and then comparing the relative phases to create a three-dimensional map of the bed. Personally, I'm looking forward to the day when we have a flock of unmanned aerial vehicles flying information behind a transmitter, each carrying a receiver, in the aerial equivalent of a 3D seismic streamer. However, until then, I think there's plenty of opportunity for improving the processing of single-phase central radar data. So this is one of my favorite radargrams. There's just so much information here. It was flown roughly along Totten's flow line, which leads to a lot of this off-nadir clutter. But I think it's possible to develop processing techniques that will highlight echoes from crevasses versus echoes from the true ice-ocean interface. And also processing techniques that will help suppress off-nadir echoes. So the multiple reflections, as you can see here, result from multipath between the airplane and ice surface, or multipath within the ice shelf. And so my postdoc took a tiny step towards improving the interpretation of the nadir ice-ocean interface based on the fact that geometrical constraints on path length mean that the existence of a maxed basal multiple and a horizon indicate that the corresponding interface must be nadir.